So we're going to start in on the next set of slides. So now we're going to be talking about chemical equilibrium. You may remember from the previous chapter that I said that chapter, kinetics, was really talking about once a reaction goes, how fast will it go? Well, equilibrium has some connection to kinetics, but it's more connected to thermodynamics, where we're basically saying, will a reaction proceed, and when it proceeds, what will the composition be? So rather than being interested in the energy gap between the reactant and the transition state, we're going to get to the point of talking more about the energy gap between the reactants and the products. So what do we mean when we're talking about equilibrium? Equilibrium is when we get to the point where a reaction and its reverse reaction proceed at the same rate. So in General Chemistry 1, we really never talked about anything like this. We just imagined every reaction was A makes B. But there are many reactions in which not only is A converting into B, B is converting to A as well. And so chemical equilibrium is going to happen in a reaction like that, where A and B are essentially interconverting at the same rate. What's happening in this picture is we're looking at a reaction between N2O4 and NO2. Here's the, oops, get this pen back online here. Here's the reaction, N2O4 making NO2, and N2O4 is a clear gas, whereas NO2 is a kind of a rusty orange color. NO2 is one of the pollutants that is put in the air by, among other things, pollution from cars. So that kind of orange color will sometimes contribute to some of the really pretty sunsets, but it's actually caused by pollutants that are like NO2. Anyway, the reason that we bring this up is this reaction is pretty easy to monitor because you can figure out what the dominant species is based on the color. If the chamber is clear, then we know that it's all N2O4. As the amount of kind of rust orange color increases, we know NO2 production is increasing. So it's a really easy reaction to monitor because of the color changes that occur. So here's the balanced reaction. N2O4 makes 2NO2. And so, like we said, in these reactions, and you can see by this arrow going in both directions, in these reactions what we want to say is that both the forward and reverse reactions are taking place. But to reach equilibrium, that means the forward and reverse reactions are taking place at the same rate. So we'll elaborate on what's going on in this graph in just a little bit, but simply put, the y-axis is rate and the x-axis is time, and one of these expressions is the rate law for the forward process, and the other one is the rate law for the reverse process. And we'll get to talking about that in just a little bit here. But what we see as this dashed line is approached is that's the point at which these rates become equal to each other. So let's talk about how we're getting those expressions and then exactly what it means once equilibrium is achieved and what we can think about with regard to that. Before going to the next slide, let's talk about the second bullet point here. It says, at equilibrium, the forward and reverse reactions are proceeding at the same rate. So the analogy that I use for this statement is, imagine you have the bathtub or sink and the drain is open and the faucet is running. But let's say that we're in a situation where the drain is open and the faucet is running, and the water level is staying consistent. So lots of stuff is happening, right? Water is filling, water is draining, but the observation of the situation is that it's static, that nothing is changing. that's the best way to think about equilibrium. Even though lots of stuff is happening, a forward reaction is happening and a reverse reaction is happening, they're happening at the same speed. Even though that's true, our observation is going to be that nothing is changing because these two rates are equal. So that's kind of being reinforced here. It says once equilibrium is achieved, the amount of each reactant and product remains constant, because even though the reactions are happening both forward and reverse, the net result is the composition of the reaction mixture doesn't change once we achieve equilibrium. And again, I think this is going to come up later as well, but see, this arrow is going forward and back to say both reactions are possible. That's new notation that we probably didn't really talk about in General Chemistry 1. Okay, so yeah, that says what I just mentioned. In a system at equilibrium, both the forward and reactions are being, and reverse reactions are being carried out. We write its reaction with a double arrow like that. Not a resonance arrow where we're pointing at both structures, but a forward half arrow and a reverse half arrow. So this is going to lead us to talking about something called the equilibrium constant. And to see the equilibrium constant, we're going to revisit some concepts from kinetics. And this will really be the major connection between kinetics and thermodynamics. After that, we kind of these two things diverge a lot. Okay, so remember we've got our overall reaction N2O4, equilibrium arrow makes 2 NO2. So go back to the kinetics chapter, and we spent a lot of time trying to figure out, based on experimental data, what the rate law would be. And at that time, I told you, you don't want to assume the coefficients in the balanced equation dictate the rate law. And that's definitely true, but that being said, when we have a really simple process, it turns out, in fact, that the coefficients in the balanced equation do dictate the rate law. So we call these simple reactions elementary processes. And if it's an elementary process, then I can get the rate law just by looking at coefficients. So in this case, we're trying to figure out the forward reaction with N2O4 as my reactant. It has a coefficient of 1, so we're going to say, on the assumption that it's an elementary process, then the exponent for the molarity of N2O4 is going to be 1, just like its coefficient. So the rate of the forward reaction is going to be the rate constant for the forward process, Kf, times the molarity of N2O4. If we do the same thing, let me go back for 1 second. If we do the same thing for the reverse reaction, it'll kind of be the same idea. So now we've got our coefficient of 2 for NO2. Assuming it's an elementary process, the exponent shows up for the molarity of NO2. And now I've got Kr, the rate constant for the reverse reaction. So Kf and Kr are not the same, right? They're describing two different processes, so there's no reason that they would be the same, but we're defining them as two separate rate constants since they shouldn't be the same. So remember what the definition of equilibrium is. The definition of equilibrium is the forward and reverse rates are equal to each other. Well, we just figured out how to express each of those, right? N2O4 makes 2NO2. The rate is K forward molarity of N2. Oops. Find the eraser here. The molarity of N2O4. And then on the other side, thinking about the opposite process, 2NO2 makes N2O4. Then we'd say the rate equals K reverse times NO2 squared. And again, the coefficient here has become the exponent there. Oh, I missed a line back here. And then the coefficient of 1 for N2O4 becomes the exponent there. So now we ultimately write this statement to say, if we're at equilibrium, these rates are equal, so these two expressions must be equal to each other. If we reorganize this to put the K terms on one side and the molarity terms on the other, this is the expression that we would get. So on the left side we have forward rate constant divided by reverse rate constant and equals the molarities of our components, and it's product up top, reactant down below, right? NO2 is up top, N2O4 is down below, so that's what we end up with. So this is how we define the equilibrium constant. We're going to say the equilibrium constant is defined as this ratio of the forward and reverse rate constants. So again, let's rewrite our equation here. N2O4 makes 2 NO2. And so now we get our overall equilibrium constant. So for a fixed temperature, the rate constant is also fixed, right? We saw that temperature can cause the rate constant to vary, but at a fixed temperature, these two values are going to be fixed, and so this ratio will be a constant at a particular temperature. In theory, that means the equilibrium constant will vary a bit with temperature, but for a fixed temperature, this will in fact be a constant. So here's something that can be tricky to keep track of. The equilibrium constant K is a capital K, and the rate constant K is a lowercase k. So you really want to be sure your two letters look very different from each other, so that you know whether you're thinking about equilibrium versus thinking about rate constant. So what we've kind of done here is generated a generic approach to building up the rate or the equilibrium constant. So to get here, we talked about the rate law of the forward process and the rate law of the reverse process, treating each as an elementary process, meaning the coefficients in the balanced equation became the exponents in the rate law. So we can kind of simplify this process going forward so that we don't need to do all of that each time. Instead, we can look at a balanced equation and immediately jump to the equilibrium constant. And so, like I had said before, we've got product in the numerator and reactant in the denominator, and the coefficient in the balanced equation becomes the exponent in the equilibrium constant expression. That pattern will always hold true, understanding that the equilibrium constant is the ratio of the forward and reverse rate constants. This pattern will always be correct. So then back to our very generic form of a reaction. So remember, the uppercase characters, those are our components, so elements, molecules, whatever they may be, and then the lowercase letters are the coefficients. So for an equilibrium process, A plus B makes C plus D with these coefficients. Now we know we can just directly write the equilibrium constant by just doing products over reactants. And here you see that we call it Kc, and the C is for concentration. We're expressing our equilibrium constant in terms of molarities, right? That's what the brackets are telling us, and that's why it's going to be Kc. There'll be a lot of different subscripts for the uppercase K for equilibrium constant, kind of depending on exactly what it is we're talking about. So this is all you really need to make sense of for the moment, is how to form the equilibrium constant from the balanced equation. But we explain why it is this format by starting from kinetics and saying equilibrium means forward and reverse rates are happening or are equal to each other. The forward and reverse reactions are happening with equal rates. And as long as that's true, that's the definition of equilibrium. And then here is our equilibrium constant. So the equilibrium constant will be satisfied numerically when we are in fact at equilibrium. So that was Kc. We can also have Kp, where for a gas phase reaction, we describe everything in terms of partial pressures. So this is saying the partial pressure of the products raised to their respective coefficient powers divided by the partial pressures of the reactants raised to their respective coefficients is the Kp value. So it'll depend what we have to decide whether we write Kc or Kp, and we may need to interconvert between the two depending on exactly what it is we're trying to do. So how would I convert between Kc for concentration and Kp for pressure? Well, the most convenient way to do this would be to go back to the ideal gas law. So PV equals nRT. Remember, P is pressure, V is volume, N is moles, T is the temperature in Kelvin, and then R is the gas constant, which I've typically used this value for PV equals nRT, 0.0821 liter atmospheres per mole per Kelvin. You would use a different base unit for pressure depending on what you're given, but this is the version I typically use, and that'll be fine for what we're talking about here. So if we rearrange PV equals nRT, N over V can be grouped together, and that's essentially moles per liter, which is molarity, right? So what we get here is essentially an interconversion between pressure and molarity, and we achieve it by multiplying by RT. So each time we have a molarity and we need to change it to a pressure or vice versa, we multiply by RT. So what we can do to create a relationship between Kp and Kc is use this expression. So let me go back for 1 second. So whenever we have a molarity and we want to, when we have molarity and want to go to pressure, we multiply that molarity by RT. Keeping in mind that the molarities could be raised to different powers depending on coefficients in the balanced equation, that's also a factor that we'll need to consider. So when we get to this expression, it says Kp equals Kc times RT to the delta N power. And this is only going to apply for things that are gases, but delta N is the moles of gas phase product minus the moles of gas phase reactant. Because every time we're converting pressure and molarity back and forth, we'll multiply by RT to whatever power applies based on the balanced equation. All right, I think it'll make more sense to actually use this equation rather than just looking at it by itself. So we'll do that over the next 2 slides. Let me scoot up the table there. Equilibrium concentrations for the reaction between carbon monoxide and molecular chlorine, meaning Cl2, to form COCl2, that's phosgene, at 74 degrees Celsius are all these molarities, 0.012, 0.054, 0.14. Calculate the equilibrium constants Kc and Kp. Well, we're given molarity already, so we should start with Kc, but let's get our balanced equation from the information in the problem. carbon monoxide, CO, reacting with Cl2, making COCl2. All of these are gases at the given temperature. So there's our balanced equation. So that means Kc is just going to equal the molarity of products over the molarity of reactants. There are no coefficients in my balanced equation, so there are no exponents in my Kc expression. Now I just put the numbers in. COCl2, it tells me 0.14 molar, carbon monoxide 0.012 molar, and chlorine 0.054 molar. So that tells me the equilibrium constant value is 220. We talked a little bit about units for the rate constant. For the equilibrium constant, we're really not concerned with what the units are. It's going to vary so much just based on the coefficients in the balanced equation. Okay, so that's part one of this question. They asked us to solve for Kc. Now we want to solve for Kp. And so here, I think in practice, seeing how it works will make it clear what we do with that equation. So Kp equals Kc times RT to the delta N. So the most important thing we need to do here is figure out what delta N is. And it's the moles of gas phase product minus the moles of gas phase reactant. So there's 1 mole on the right side, 2 moles on the left side. So we get delta N equals -1, right? 1 mole of COCl2 minus 1 mole of CO minus 1 mole of Cl2 gives us -1. So that means Kp equals Kc times RT to the -1. Well, here's our R value, right, in liter atmosphere per mole Kelvin. Here's our value in Kelvin for the temperature, right? We need to do that. So 74 plus 273 gives me 347 Kelvin. And now I'm ready to plug in. So 220 times RT, parentheses, raised to the -1, gives me my Kp value. So I have Kp and Kc. So the reason I would like to be able to have either one of these is depending on what the data I have tells me. If the data is in terms of pressure, then I want Kp. If the data is in terms of molarity, I want Kc. But I want to be able to interconvert the two, so depending on what data I'm provided, I can have the correct equilibrium constant in place. Okay, let's do 2 more practice problems, and then I think that's good for this first video to get us going on the equilibrium stuff. Okay, first question here says, the reaction below has a Kc of 0.013 at 1005 Kelvin. Convert to Kp. So we know Kp equals Kc times RT to the delta N power. So really, we just need to figure out delta N. If I do look at my expression here, or the balanced equation, there are 2 moles of gas on the product side, and then a total of 3 moles of gas on the reactant side. So delta N would be -1. So make sure you're only counting things in the gas phase, because the only ones we're going to need to follow the protocol for converting molarity to pressure for are going to be things in the gas phase. Okay, so let's plug in what we know, and we should be able to solve. So Kp equals Kc, which is given as 0.013, times RT to the -1, so 0.0821. The temperature is 1005, and that portion is raised to the -1 power. Okay, so let's calculate this real quick. And I got 1.58 times 10 to the -4. All right, so that's our Kp value for the first one. All right, how about the next one? In this case, they give us Kp and they're asking for Kc. So things are going to change a little bit because it'll be Kc equals Kp divided by RT to the delta N. Well, delta N in this case, again, products minus reactants, everything's in the gas phase, so 2 minus 4, that's negative 2. So that means Kc equals Kp, which is 1.45 times 10 to the negative 5, divided by RT to the delta N, 0.0821 liter atmosphere per mole Kelvin, times the temperature in Kelvin, 510, and that's raised to the negative 2 power, but it's in the denominator, so really it's the second power, but in the numerator. So let's see what we get here. Okay, I got 0.0254. So a fair thing to ask here is what are we calculating? What do these numbers mean? So when I see, for example, this Kc value or this Kp value, what is it telling me? Well, it's related to the balanced equation, and it's telling us the numerical value for that equilibrium constant. So generally speaking, this number is telling me what does the composition of the reaction mixture look like at equilibrium. And generally what we can say is this: if the number is large in magnitude, then products dominate at equilibrium. If the number is small in magnitude, then reactants dominate at equilibrium. What do I mean by dominate? It means that's the major component. Since the ratio is products divided by reactants, if it's a big number, then the molarity of products is larger than the molarity of reactants, more likely than not. And if it's a small number, then the molarity of reactants is bigger than the molarity of products. So that's what we want to be able to say when we look at these numbers. And more broadly than that, if a reaction favors products, then it's probably energetically downhill, meaning products are lower in energy than reactants. If a reaction favors the reactants, then it's probably uphill in energy, meaning the reactants are lower in energy than the products. We'll revisit those concepts as we get into more detail in this chapter, but just trying to give you the big picture as we start in here, especially because we're just looking at these numbers and I want you to be able to make a little bit of sense of what these numbers are really telling us. So let's go ahead and stop at this slide.